Um, just before we get into this video, I would like to apologize for my inconsistently lately. Life's been kind of busy, exams and stuff. But, we're back on the grind, back on it. So today we're going to be talking more about um, electron shielding and electron interaction with the positive nucleus of atoms. We're going to be talking about atomic radii, ionic radii, and we're going to also be using that information to talk a bit more about electronegativities and trends across first ionization states. So, to begin with, we're going to talk about some general concepts to keep in mind. So, I'm going to label this as, let's label this as general concepts. So when we're thinking about electron attraction to a nucleus, there's a couple concepts you want to keep in mind. So let me jot this down. Electron attraction to nucleus depends on three factors. The first factor is how many protons are in the nucleus. And so this term is called our nuclear charge. For example, calcium has 20 protons, which means its nuclear charge is 20. There are 20 positive forces acting within the nucleus of the calcium atom. The second term, or the second condition, is how far your valence electrons are from the nucleus. And so this can also be deduced to the number of shells. Think about it. An atom with more shells means that the outermost valence electron is being shielded by a lot of other electrons. So let me illustrate this. Say I had our trusty sodium. That's sodium. Sodium looks a bit like this. Compare this to hydrogen. Note, this hydrogen is very close to the positive nucleus, meaning it is very strongly relatively strongly attached or attracted to the nucleus because it's very close, as opposed to this electron, which isn't very close. All the other electrons beneath this outermost electron, these electrons are called shielding electrons, and these shielding electrons essentially consume the positive charge of the nucleus before it can get to this outermost electron. This means removing this electron is easier than removing this electron. Sorry about the notification there, that's just my friend. Because the outermost further electron here is not as influenced by the positive charge of the nucleus as the electron here is. And that brings me to my third condition. My third condition is 3. How many core electrons are between the outer electron and the core? And the nucleus. So going back to our sodium example, these electrons in between our valence and nucleus, these electrons are called our core electrons, and our core electrons are shielding the valence electrons from the positive charge of the nucleus. And so the more core electrons you have, the weaker the interaction between your valence electron on the outermost shell and the positive charge of the nucleus. So again, key concepts: electron attraction to nucleus depends on nuclear charge. A greater nuclear charge means a stronger positive nucleic force, which acts more strongly on the outermost electron. Your second condition is how far your valence electrons are from the nucleus, so the number of shells. More number of shells means more core electrons, which means your outermost valence electron isn't as heavily influenced by the nucleic charge of the nucleus. And third is how many core electrons are between the outer electrons and the nucleus. So more core electrons means your outer electron isn't as influenced by the positive nuclear charge. So there are three general concepts you want to remember. Moving on to atomic radii. Right here, if we move on, atomic radii. So there's also a couple of things you'll want to remember moving into atomic radii. So the first thing is the atomic radius is the distance from the nucleus to the outermost electron. So if I illustrate this, say I had lithium, the atomic radius is the distance from the nucleus. If we call this the nucleus to the outermost electron, this is your atomic radius, okay? Since the position of the outermost electron, since the position of the outermost electron can never be known precisely, because remember, we can never know where electron is. The atomic radius, according to the IB, is defined as half the distance between the nuclei of two bonded atoms of the same elements. So if I had, what it's saying is if I had a diatomic element like oxygen, the atomic radius is defined as half the distance between the nuclei of two bonded elements of the same kind. So if this is our distance from nucleus to nucleus, our radius is only half of that. Hopefully that makes a bit more sense. And another thing you'll want to consider is the trends, okay? So in a unit called periodicity, which I'm sure you guys will go over soon, you can actually use the periodic table to determine trends. And so the trend here is that atomic radius increases going down a group. So let's actually take a look at that. If you notice, going down a group, you actually get more shells. Here you have one shell, here you have two shell, here you have three shell, here you have four shell, so on and so forth. As you have more shells, the atomic radius gets bigger because electrons are added to energy levels farther away from the nucleus. So if I have more shells, my distance from the nucleus to the outermost electron is actually systematically increasing. So if I had, went back to my example here, the distance with a sodium atom with 3 shells is much greater than the atomic radius of electron with just 1 shell. So as shells increase, as you go down a group, the atomic radius also increases. So that's something you'll want to remember. Ionic radii is a similar concept. So let me show you guys. So with ionic radii, it's the same thing. You're going to want to remember 2 key terms. Cations are positively charged ions from the loss of electrons. Anions are negatively charged ions from the gain of electrons. So when a cation becomes a cation, when an atom gains an electron, what happens is cations become smaller than the metal atoms from which they formed, because now there are fewer electrons than protons in one less shell of electrons. So when a cation loses electrons, lesser shells, which decreases atomic radii. And we also have less electrons, more protons. And if we have a net charge where protons are greater than electrons, the nuclear force, the positive nuclear force of the atom can now act more favorably upon the electrons, which means the atom shrinks. So let me show you an example. If I had a sodium, we went back to our sodium, if my sodium all of a sudden lost an electron, right, it formed a positive 1 charge, it lost an electron, this is what it looks like now. The sodium, it loses a shell, and because it's more positive now, there's a more positive charge that is acting on less electrons, the electrons actually are brought closer to the nucleus. And as it does this, the atomic radii decreases. So the radii decreases. So that's something you can remember. For anions, it's the same but in reverse. If I can go here. For anions, anions are larger than the non-metal atoms from which they are formed because more electrons are present than protons. So these ones would be smaller than metal. These ones would be larger than non-metal. And here it would be because there are more electrons than protons. And when there are more electrons than protons, the positive nuclear charge of the nucleus has to now act on more electrons. And because of this, the positive nuclear charge of the nucleus is acting less favorably on the electrons, which means they are not as pulled into the center. Because they're not as pulled into the center, now they expand and the size expands as well. So that's a bit more about radius. So moving on from radii and electron attraction, we can now transition a bit more into first ionization energies. And firstly, what is a first ionization energy? A first ionization energy, pretty much, a first ionization energy is the energy to remove one outer electron from a gaseous atom. The IB likes to denote this. The IB typically likes to denote this as this. So if I have a gaseous atom, we can denote it as X(G). And when we remove one electron, what happens is it becomes X of, when we remove one, it becomes a positive charge, and we remove an electron. When we remove an electron, it becomes positive, and this was once neutral. Oops. Shout out to my boy Lucas, but we're going to have to mute you for now. So this is kind of how the IB likes to denote first ionization energies. And the trend here, the periodicity, you will learn about this later, but the trend is as you go down a group, the first ionization energy decreases. So let's take a look at that. What happens as we go down a group? Well, as we go down a group, we have more shells. As we have more shells, we have more shielding electrons, right? Reference to the general concepts you should keep in mind. As you have more shielding electrons, the positive nuclear charge of the nucleus can't act as much on the electrons, which means the electrons on the outermost valence shell are relatively liberated. If we go back to our sodium atom and we want to ionize the sodium atom, we look at our valence electron right here in green. It's right here in green. If we look at that, and compared to that of the hydrogen, what we can see is that this ion here is more liberated in that it's not as influenced by the nuclear charge as, say, this atom right here, which is closer to the nucleus. So essentially, as you go down a group, you cultivate more shells, and as you cultivate more shells in the atom, that valence electron isn't as restricted by its electrostatic attraction to the nucleus. And this is what you notice here. Noble gases typically have the highest ionization energies because their outermost valence electrons are very restricted. They're restricted because they are present in a shell where the protons and the positive charge of the nucleus act very greatly upon them. But if we look at other metallic species like lithium and sodium, they actually contain a valence electron. They contain a valence electron on the outermost valence shell that is furthest away from the nucleus and is more liberated because it isn't as influenced by the positive charge of the nucleus. This means it requires less energy to liberate that electron and ionize the species. So let's illustrate that. Say I had a sodium, because we all love sodium. We're all salty people. Say I had sodium, right? And let's compare that to, say, a noble gas like neon. If you look at this electron, it's very far away from the nucleus, and it isn't actually being, it's not very influenced by the positive charge of the nucleus. Whereas here, all these electrons are equally influenced by the nucleus. So removing an electron from here would take exponentially more energy than moving it from here, because this electron is pretty much liberated. It's liberated because it isn't influenced by the charge of the nucleus as much as it would be in the neon atom. So this is what describes our first ionization trends. As we go down a group, as we increase the shell number, as we increase the core electrons, our valence electron becomes more liberated and easier to remove, hence lower ionization energies. But as we approach noble gases being the occupancy of a complete octet, our proton number increases, as our proton number increases, our nuclear positive charge increases, and as our nuclear positive charge increases, the influence the nucleus has on the electron increases, and so it takes more energy to liberate an electron. So hopefully that helped a bit. If you have any questions, feel free to leave them in the comments, and all the best.